Yeah, right. So can you see how this function, it actually hasn't printed anything. Oh, sorry, it doesn't actually return anything. It prints something. So what's going on here is that when we run the function, we run the main. So this is our main block of code. Okay. And then we call average of two function. Python goes to find where the average of two has been defined, passes in A as 1, B as 10, sum will be 11, the average will be 2, it will be 11 2, so that's 5.5. And inside the function, it executes this print block. So essentially, the function doesn't return anything, right? It just prints it within the function. So this is another way that you can use a function. So it's literally some function, like some operation that you want to be done. So for example, here, oh, by the way, technically the function does return something. It's a none type that we've been talking about earlier. So over here, average of two will kind of be replaced by none. But then that doesn't matter because it's not stored anywhere. So we kind of just lose the return value. So let's explore some more. If you have a print inside the function, all it does is that it displays the value to the caller. So when you call the function, it will print the result to the terminal, which is what you can see. If you were to return, it sends a value back in place of call. Right. So if we look at this example, what's happened is that we call this function, okay, it returns 5.5. So rather than here being average of 2, this is being replaced with 5.5. So that's what return does. It replaces. And then in the main function, that's where we do the printing because we've stored the 5.5 in the average bucket. And now we're able to display that using the print. As opposed to this function where we're calling this, okay, because it's, and it prints it within the function. And because there's no return, this will be replaced as none, but the line execution is not saved anywhere, so it just keeps going. So we're going to do a couple more examples now of the differences between print and return. So if we were to call this function, what will happen? So anyone think A, B, C, D? All right, we go again. Just put your hands up for the option. Okay, A. Yeah, okay. B. One C. D. Okay, is A. So most people got it right. So what's happening here is that remember when we run the block, we actually kind of skip this part, right? We only look for this part when we are calling the function. So this is the only part that's getting executed. When we execute greet Alice, what's happening is that we're passing Alice into the function. Okay, so that name here is going to be replaced by Alice. So essentially, the function will run print hello plus name, which is Alice, because we pass Alice into the function plus the exclamation mark. So what's going to happen is it's going to print hello Alice exclamation mark. So why doesn't it do B? Any guesses? Yeah, I mean, so if we print this function, we're going to print a none type. So essentially, the none has replaced this block. But because we're not doing anything with it, it kind of just gets lost. No hello Alice none, because we're not printing this function. It wouldn't throw an error as well because what we've done here is perfectly reasonable. What about this? So hands up for A, B, C, D. So the answer is C. Because over here, we have add 3 and 5. So again, we're only executing this part when we run the block. So the result is equal to add 3, 5. So the Python's trying to fit, okay, what should I put inside the bucket called result? It looks for the add function, which is here. So it passes A as 3, B as 5. So it returns 3 plus 5, which is 8. And recall how when you return, you're essentially replacing the original function call with whatever you're returning. So now this bucket holds 8. And when you print result, you're able to print 8. What about this one? Okay. Hands up for A, B, C, D. Okay. So what we've got here is that, again, we're executing this to blocks. So result, okay, we made a bucket called result, and then we're now trying to figure out what to put in here. And then we go to the function add 2, 3. So Python finds this, passes A for 2, B for 3, and then inside the function, we print A plus B. So that's 2 plus 3. So that means that the first thing that pops on the terminal will actually be 5, because within the function, it prints a 5. But then the function ends. So when you don't return anything, recall how Python does a none for you. So that means that add 2, 3 will be replaced by none. Okay, so none is being stored inside the bucket called result. So when you print result, you actually print none. So it will be 5 none. So even though this function, see how this function is being called, and even though I guess on the surface, it's as if we're trying to store the result into here, this is actually a mistake because you didn't return anything. So the result bucket, if you ever want to use it again, it wouldn't hold 5. It will hold nothing. It will hold none. But the reason you print 5 anyways is because inside the function, when you execute this function, everything inside here runs, right? So that's all the function is doing. The function is printing a 5 for you. So technically it should be 5, and then the new line, there will be none. What about this? Okay, so hands up for A, B, C, D. Okay, so everyone got it right there. So basically when we print this, Python's looking for what are we printing? So it goes to this function call. So we pass n is equal to 4. And what the function returns is 4 mod 2. So it's basically asking for what is the remainder when you divide 4 by 2? And because it perfectly divides with no remainder, you will get 0 here. So basically this will be replaced by 0, and this is 0. So it's evaluating whether 0 is the same as 0. It is. So this will be replaced by true. So you're basically, and then remember when we return, we're replacing this whole thing with whatever we're returning. So we'll be returning true. and then true will be printed on the terminal. If you were to just return n mod 2, so without this, that means that we will be able to print a 0. So that will be returning whatever the remainder is. Last one. Okay. Hands up for A, B, C, D, E. Okay. So what's happening here is that this function does both multiply and print, right? So when we call this, we assign a bucket called stored result, and we need to store whatever the output of this is. So Python passes 3 and 4 into this function. And do you remember the variable scopes that we were talking about before? This result only exists within this function. So we have a new variable called result is equal to 3 times 4, which is 12. And then we print that out. So the first line of output will be 12 here. And then it will return 12 as well. So essentially, this thing is going to get replaced by 12. So 12 has become a stored result. And when you print the stored result, that will be 12 again. So 12, 12 is the answer. So super important points to note here is that when you print, it just kind of keeps going. But when you return, that is when you're exiting out of the function. So a function can have multiple exit points. You can have control float, right? Sometimes you can return on one condition, another else can be returning something else. But as soon as you return a function, that's when the function call becomes replaced by that return, and the function just goes away. And then all your variables within the function are also gone, which is why it's so important to store whatever you're returning into your own variable. So this variable is accessible, is a global scope, right? It's accessible everywhere in your code. But this result, it only exists within these 3 lines of the function. So if we didn't have the return, which is what happened here, we call the add to 3, we print it, so that will be a 5 first. And then, because we didn't return anything, Python will replace the function call with none. So you'll be printing none here. So it's really important to store everything function calls. So this is our example of making a BMR function, which makes it so much easier, right? So we can have weight, height, age, and then a sex thing. So if it's capital M, we use the formula for men, and otherwise we use a formula for women. And then we return. So see how we're storing this here as either so the BMR kilocalorie is either this or this, and we're returning that result. So again, if you see this just in the code somewhere, you have no idea what it's referring to. And it's so much more less elegant than just calculate BMR, weight, height, age, sex. So let's have a go writing your own function. We've already done a few functions before, but this is unique in that you're allowed to pass in a parameter, which makes your function know what's going outside the program. So I think in the notebook earlier, there's actually a template for that. You can just code it in there if you want. Okay, so this should be hopefully pretty simple, but essentially we use def to tell Python is a function. We use the lowercase snake case to denote a function is a convention for a function. What we're passing in is an age, which is a variable that only exists inside this function. So what is our maximum heart rate? Is 220 minus the age, and we return this. So basically, I know that we've gone through a few examples of functions that print, but realistically, most of the time you use function, you should return it because we need to be using that value somewhere later, probably. You don't want to be printing to console where essentially, even though we can see it, that value has been lost everywhere else in the program. And what you can also do is rather than return maximum heart rate, this is another variable called maximum heart rate. We can actually just return 220 minus age as well. So Python will just calculate what's 220 minus your age and then just return that. So same as this, we can actually have a return statement here if sex is m. So just return all this rather than storing into a new variable. And we can have return all this block as well. Or we can return the n is up to personal preference. So right now, our function is a problem. So it works if you just call it in your code. But what if you enter like, I don't know, maximum heart rate and your age is like -10? Or if you enter like 300 as your age, you're gonna have a heart rate of -80. So let's try to foolproof our function that basically only accepts input from 1 to 115 inclusive. If the answer isn't that, it will ask the user to please enter age between 1 and 115. So it doesn't need to be a while loop, just print it once and it can exit. Okay, so how we can do this is basically do a check before we return something. So the maximum heart rate, if it's not inside, if it's not within 1 to 115, it will return. Please enter an age between 1 and 115. Otherwise, it's just going to return the max heart rate. So you can also make it with, so make sure that brackets, I've seen people have the mistake of not having brackets and Python kind of gets confused. So it's a really good habit to wrap all your individual conditions in brackets. And it also makes it clear for you as well, just so you know that this is a block, this is another condition that is checking. So has anyone, you know how I have some test cases on the functions here? Has anyone printed a none a lot along with the reject answer? Yeah, so for this one, if we were to do, say, we'll do the reject one here. So if 1 is less than equal to the age, less than equal to 115, so that means it's another way. So this means that the function's okay. We can return 220 minus age. Otherwise, that means that the input is not viable. We can print, say, not allowed. So when I run this, I should print a lot of rejects. But also, there will be some nones. Just waiting for Colab to run, connecting to Google's computers right now. So see here, that's the first line. It should print 210, 201, which is fine because that's allowed. This is fine as well. But this is not within 1 to 115, right? So we print not allowed. But it also prints none as well for some reason. Why does it do that? Has anyone run to this as well on your own code? Yeah. Did anyone have a fix for that to not print the none every time? Yeah, exactly. So you can return it instead, right? So what's happening here when I call this is that Python is looking for something to print. The print thing is whatever the function returns. So when you put 230 into here, okay, is it within the limit? No. So it executes the else block. It prints not allowed, which is what we see here. And then it exits. But remember how it doesn't have a return statement. So Python automatically replaces whatever we had here with a non-type. So this print was executed within the function. And then when the function is done, after executes is not allowed, it will replace this with the non-type. So this line will execute the none. Does that make sense why there's two parts? So again, same for everything else, right? And how we can do this is that we can just change a print to a return. And again, this is how typically we do it. Otherwise, because it's really important for the functions to return the same type every time. Like you can't be returning none sometimes and returning numbers or strings, right? So in this case, we're trying to print the result so we can actually just return not allowed. And that fixes all the issues. So super important to understand the difference between return and print. Okay. Do you have any other problems? Has anyone tried to play around with your code or even your friend's code? Like, how else can we break it? So I've had a few test cases here, which is basically the next most important thing. So how do you know that your functions work? You need to write a bunch of test cases. So I've done it here, but later on, you're going to need to write your own test cases. So I try to break the code by having large numbers, small numbers. And notice how I check edge cases. So 0 should reject. 0.5 because it's less than 1, it should reject. 1 should be fine. Okay, this is another edge case. So because it's inclusive of 1 to 115, it should be fine. How else can we break this code? Anyone want to try to break my function? What do I need to input to break it? Huh? Yeah, right. What if someone doesn't know? They put like 4 in here. What happened? What's happening here? So you think you should return not allowed, right? Because it's not within that. But remember how comparison between data types is a huge problem? So we're trying to compare one with a string, which is not allowed. So I guess it doesn't print not allowed, it throws an error. So it's just telling you that this operator doesn't support comparison of integer and string. So maybe we can, if you want to go further, you can check rather than just this check, you can also check that the input is a number. Okay, so make sure to, yeah, and this is another reason why functions are so good, is because you can test it super easily like this. I just copy and paste a bunch of this and change the numbers. And from that, what I figured out was that, okay, I need to change the print statement to return of the string. Otherwise, it will print out nuns, which is definitely not what we want. So function is allowed to test it individually. And again, modular code is good code. So far we have function that return anything like a none, function return number, but you can also print return other types, so any other type. So you can return a Boolean as well. So we've been using it a lot already. This is not a function technically, but this is replace a Boolean. This replaces a Boolean, and or is another Boolean return, because the evaluate is true if either of these statements are true. So this is an example. A function is odd. I pass a number and I check whether the remainder of this number is 1. If it is, then it will be odd. So this is actually, this is called a predicate function. So it's a special type of function called predicate. And it's basically, you can ask, it's like you're asking the program something, like whether you want to know something true or false. So for example, if you want to code a tic-tac-toe, you can have one called is over. Is this game over? No. But false, it will be replaced as false. How about this? Yeah, so it'll be true. So basically, it's like you can input actually. So right now we can only input like 2 or 3, but from tomorrow you'll be able to input like huge amounts of data into the function and again make it do a lot more. What about this? A bit hard to see, but there's actually a really cool sequence of moves like Easter egg. If you guys wanna have a look. Okay. Anyways, so this is another function that can return. So I've written it's a toll. So if the height is greater than 180, we define as toll. So is this true here? Yeah, it's not. So 179 isn't. What about this? Yeah, because poor guy, he is not greater than or equal to. So it will be no. So again, for functions and these comparisons, so much of your time will be spent trying to work out these edge cases. So an edge case is basically between the border of true and false. So see how here, like you run to test 180, is that fine? And before, you know how the test cases I wrote is like 115. So make sure the boundaries between decisions is fine. So remember the divisibility by 7 thing at the start? How much nicer is it to write as a function? Because before we just had to do the mod 7 every single time, right? Let's write a function now that returns true if the number is divisible by 7 and false otherwise. And when you've done that, try to make a more versatile function that can take 2 inputs, the number to check and the divisor to see if it's divisible. So it'd be like 245, comma 7. That's how you would call the function. Oh, okay, so has everyone had a go at the divisible functions? Okay, so the first thing is pretty easy, right? You can just return this straight away. So num mod 7 is equal to 0, then true. And to make it work for everything, all you need to do is to replace a 7 with another parameter called divisor, and you'll have it. So pretty simple. And other things we can write are HB, for example. I've seen has everyone had go at this as well? Pretty much. No, okay. Let's have it. We can do this as well. So we can check if the hemoglobin is within 125 to 185 for men, that for women, and the input is hemoglobin and sex, which is true for male and false for female. Okay, so we keep going now. Basically, what this program here has got is that if sex, so I know you can do if sex is equal to male equals to true. We actually just write if sex. So that means that if it's male, because sex is true, right? If it's male. So this is equivalent to if sex is equal to true. That means that we run this block. And otherwise, that means that it will be female. So you don't have to write if sex is equal to false or if not true. Then you do everything else here. But notice how in my function, I return true, false, true, false. That makes the function really useful because that's what a predicate function needs to do. If you return like normal or abnormal, that's fine. You can use it as the end product. But to build really good modular code, what we probably gonna need sometimes is like writing something like if someone's HB is normal. Imagine the flow chart, right? Like if someone's HB is normal, let's say their HB is this, and they're female. If you don't return a true and false, you can't run if else statements, so you can't ask the function anything else. So it's really important if you want to build a predicate function, rather than returning some string of text, you return something that you're able to use down the line, which is a true false. But this is also what you can do. So 4 lines of code. Has anyone done this? Yeah, so you can actually return this straight away because Python evaluates for a male, for example, if the hemoglobin is within 125 and 185. So if it is, it just replaces as true. Otherwise, it replaces as false. So see the difference? This is like a lot of line. And frankly, it's kind of confusing with so many indents. But this looks so much cleaner. More readable and elegant code. So in the future for predicates, this is generally the way to go. We don't like to return true unless we have to. So usually we try to return this condition straight away. So try to use this in the future. Okay. So that's it for some of the own functions. But part of the reason that Python is so great for the scientific community is because of how good the library support is. We've already seen the random, we've already seen the math, but there's also external libraries that you can install. They can basically let you do anything, especially in the deep learning sphere. So this is something I built way earlier, and this is like kind of facial recognition thing. So running on Colab. And this is back then I didn't even know any of the math. I only knew Python and ChatGPT. But basically only need 50 images per person. It's like a classifier. So basically you can capture and then it will recognize if it's someone I've trained, someone not, and someone who's trained. So at the end it shows, wait, I had to get really close. Yeah. At the end. So basically, this is just using someone else's library with ChatGPT and without knowing any of the things before. And it's only 50 images, so it's pretty clever. This is basically what you do. So just you can before the reason I think you can do so much now is because before this wouldn't make any sense, right? If you look at this code, it would just be completely might as well being a foreign language. But it's only been 2 days, and I think everything here is almost readable. Which is so cool. Because the first part, all we need to do is to import some libraries. Right, so that's all that done. All this is a function. And this function, the only job is to load the images from the folder into the just load it. And then the images is stored as a list. So we're going to go into lists tomorrow and how that's a really good way to handle a lot of data. And all this is a for loop. So can you see how rather than for I in range, because range gives us like 0, 1, 2, 3, all this is for every file in our folder. right? And this is another function. Is from the OS library, operating systems library, it gets all the list directions, so all the files in that photo, and then we just loop through everything. And then we're using more functions. So remember how this low image file function is from the face recognition library. And then it returns all the images in the list form. So you can honestly try this, and there will be some things you don't know yet, but ChatGPT can explain most of it. And after tomorrow, especially the data structures, all this should be really, really readable. So how do we use other people's functions? Say we're going to use the print function, right? And it's something we're taking for granted, but there's actually a lot of things you can do with the print function. So it's easier, like W3 Schools is really good, Real Python's really good. They explain it pretty well, make it simple. But the official docs are usually the most comprehensive. Then essentially how the print function does. And by the way, this is something you never need to memorize, right? Like for example, if you come back to Python in 5 months, you're not gonna need to remember exactly what to put for the print. You can just read it up. This is not the important thing. The important thing is understanding the logic and how to write a program. So looking at this is Python's own definition of the print function. And it looks really complicated, but essentially what they've got is that, you know how our arguments, we call them positional arguments. So we know that if we have the BMR thing here, we know that the first thing has to be the weight, second thing has to be the height, the third thing has to be the age, and then the sex. But that's really hard to remember, right? If you have a function that can take there's function that takes 20, even 100 possible parameters. How are you going to remember the exact position? So something else we can do to make our functions even more powerful and more easy to use, more importantly for the end user, is to use keyword arguments. So basically, that's what Python does. In a prototype, they can have sep, which is what's separating how you end. This means ending with a new line. And some other variables that, some other parameters we won't go into today. But basically, all it is a function. These are the input parameters because there's so many that they don't expect you to remember the order. You just need to know how to call it. So, for example, here, what we can do is we can also use keywords as arguments. So, for example, before it was 71, 75, 75, you can actually do this as well, which seems like a waste of time because you're typing more letters now. But you can also do it. See how I'm doing sex first and then height and then age and then weight. So essentially, you don't have to recall the exact order, which makes it a lot more user-friendly. Because let's say before there was no safeguarding, you accidentally put 25 for the weight, and then you're gonna screw your whole function up. So yeah, this works as well because we're using keyword arguments. So how it is you call it and then you need to know the parameters, which is weight, the variables is weight, height, age, and sex, and you just assign it to a number essentially. And order no longer matters. You might see some stars as well in some other people's function definition. And all that means is that it accepts any number of inputs. Do you remember how for print, we can do print hello, Alice, explanation mark, like this? Basically, what's happening here is that this star tells print to accept any number of strings and it's fine. So it doesn't have to be one thing, it can just be any number of things. So this will join together as print as hello Alice explanation mark. So we'll write functions like this is but then just in case you see someone else's definition for the star, that's what always referring to. So for example, we do the quick brown fox. The print will do the quick brown fox like this because print can accept any number of arguments. In this case, we put 4 arguments in. And what this means, and see how their arguments also define the parameters, but also equal sign. So what this means is that this is a default. So if the user doesn't specify these, for example, see how we use print like this, and we didn't specify the sep, the end, the file, the flush. So it just knows that we want to put a space in between your arguments. It wants to move the cursor to a new line after you print, so on and so forth. So again, this is only for print, which has been using for so many. Like all the functions, if you read the docs, have a lot more things to do, have a lot more abilities they can do with them. So this is how essentially we read the docs. So you need to be comfortable reading that. So even though this looks pretty scary, if you go through all that, it shouldn't be too bad. So let's have a look at let's have a go using some other people's modules. So using the Python math module, let's write the following functions. So a function for circle area, which takes input the radius, and a function for x log 5, which basically returns x times log base 5 x. And also find the greatest common divisor of these two super long numbers. So to do that, you're going to need to search up Python math module and read the docs to find everything that you need. Okay. Okay, so we're gonna keep going now. Hello? Okay, we're gonna keep going now. So to do this math module, actually it'll be a good challenge to try to code your own GCD, make your own greatest common denominator. There are algorithms for that, so good luck, boys. Trying to hard code it yourself, but it's way easier to use theirs, right? So what this is we need to find pi from the so this isn't a function, this is just a variable that basically is in the math module. So this will be more decimal places than you ever need. And it's a lot easier than having to, hard code your own value for pi. For this one, to find log base 5, we need to go to the math module. So by the way, where we find the constants is here. So these are all the constants that you might need. And then to find the log, just try to control F log. And you can see there's a lot of different types. So this is a default. If you don't do anything, it's going to be just base E. But then see how what this means is that you can optionally have a base. So you can do x comma 5 to do a log of base 5. And these are more like, for example, log of base 10 is this. This is another way to do power rather than exponential. And then lastly, for GCD, what this means is star means you can accept as many inputs as you want. So you can put as many inputs here. So for example, if you want the greatest common denominator of divides of 3 numbers, you can put that in. If you want the greatest thing for 5 numbers, you can do that as well. Okay. So this is something we've introduced already yesterday, but it's very important in terms of scope. So now that we've done functions in more detail, let's just have a quick review of what scopes refer to. So what a scope is the region of code that your variable can be accessed from. Imagine the house is your whole program, and you create a function where inside the function you have a is equal to 1. This a is equal to 1 exists only within that function. You cannot access it everywhere else in your code, which is really good because you don't want all the variable names to be jumbled up. You want the code to be very modular and independent from other functions. So for example, if you run a print A, you will have a name error because it's trying to find A, but it hasn't been defined anywhere else except for your function. So the rest of the program has no idea what A is. So having a look at this, what would this print? Yeah, 1, right? Because we call to myfunc. Myfunc doesn't even take any input. So inside of it, A is equal to 1, and then it prints A, which is 1. What about this? Error. You can see that here. Remember how the yellow squiggly line means something wrong? You hover over to find out that is A has never been defined. So basically, this is the only part of the code that you see, print A. Now, I know we define a function. If you control F, you will find an A somewhere, but it's only within these 2 lines that A exists. So basically right now, it's got no idea what A is, and therefore will throw an error. So since B is defined, so what about this? So B is equal to 2, and then we print B. And then we call the my function. So that's the definition, and this is my function. Will we print it here? 2, hands up for 2. Hands up for nothing. Yeah, so what's happening here is that when you call the myfunc, it will go into here to look for it, and then it will try to print B. Right, and the reason this is fine is because this is, remember, a global scope. So your function actually can access. So it's kind of like a two-way street, right? Because you define this in a global scope, you define this outside the function. The function can access anything in here, in the outside part, right? So that's why it works. But it's not the other way around. So in this case, do I have it? Okay. Oh yeah, I think I had like, oh yeah, so this is in this game. So I'm using A here, kind of confusing, sorry. But A is a global variable everywhere of the program. So, your function is only one group in the whole program, right? So because you define A equals 1 outside, then every single part of the program has access to what A is. It's only any variable that you define inside the program that isn't accessible outside. So it's like a one-way street. This will be printed. Two is actually 2 and 2. Oh, wait, it's just 2, sorry. Because we never called them myfunc. Okay. I fell to my own trap. Yeah, so this function never gets executed, right? Because we never called it. So yeah, it's just 2. Great. So why is scope so important? We already talked about this before. Avoiding naming conflicts. Like if you have the same variable name in multiple functions, that's fine. Imagine if you go to your contacts and everyone in the world is searchable. Like that's ridiculous, right? And very creepy as well. So basically it allows you to define parts of the function where different variables are accessible. Modular code that don't interfere with each other. So any num in one function doesn't interfere with your num in another function. So remember the example I gave yesterday about if you have a multiply function that takes num1 and num2, and you have another function that takes num1, num2. Imagine the chaos if you need like one num1, num2, and then num3, num4. So you can actually name the same thing without affecting each other. So you can have word pair in one function and then word pairs in another. It's really confusing. So this is the last part, kind of extending from scopes. It's the problems of mutability. So let's have a look here. Are they all the same X? Yeah? Yeah, go. No. Yeah. So I've actually color coded this. This X is actually different to this X. So these X's, remember how whenever you introduce anything to the function, when you introduce the variable to the function, it only exists within the function. So now you kind of like overwritten. So your function, imagine that, even though it technically has access to outside X, it will prioritize whatever's inside. That makes sense. So this is a different X. Imagine a blue X and a red X. Even though they're named the same, they're stored in completely different parts of the memory. So, let's say that this is your computer's memory, right? There might be the one X is here, one X is there. They're completely independent. So, what about this? So, we have X equals to 5. We print before the function call. And then what would this give? Okay, so I can't get away. But this is 5, right? So again, we haven't even called the function yet. So X is equal to 5 right now. We print before the function call, X is equal to 5. Okay. And then I call the modify value function, which takes in the input, makes X equals to 10, and then we print something. So what will we print it here? Hands up for 5. Hands up for 5 if you think this function will print a 5. Hands up for 10. Yeah, good. So basically, initially we print X equals to 5 here, and then we modify value. So we pass 5 into here. So this is now a 5. So do I have that? Okay, so what that means is that in here, there will be a x equals to 5, right? But remember how this is different? So what's actually happening is that you have a 5, x equals to 5, so a bucket called x, and it stores 5. But when you enter the function, it's actually creating another bucket called x as well, but this only exists within the function. Afterwards, your computer just gets rid of it. So it will overwrite. So x initially 5, and then it will overwrite that 5 as a 10, and then print inside the function x is equal to 10. And now, even though you modify this x, remember how this x is somewhere else, right? So after you leave the function, x is equal to, what will be printed here? 5 or 10? Yeah, 5. Yeah, because what's happening is that this x, right, is completely different to the x in the global scope. So even though we're modifying this x, we're only modifying on a copy of what's passed in. So it's like you have a bucket called x equals to 5. Rather than the function kind of dipping into that bucket to modify it, it's not going to do that. It's creating a new bucket called x, which only exists within the function, and then that's initially has 5 because we passed in the 5. It's overwritten as 10, so that new bucket has a 10. And then after you leave it, that value is lost because we're not returning anything, right? Everything inside a function will be lost if you don't return anything. So you'll print x equals to 5. So this is also called x is passed in by value. And this is a really important primer for tomorrow because when we deal with more advanced data structures, it's actually treated separately. So just keep that in mind. Right now, it's creating a separate bucket called x. So yeah, essentially, the 5 gets passed in. Initially, x equals to 5, but it's immediately overwritten by the function as x equals to 10. And there's a separate bucket. The function prints x is equal to 5. And remember how the x is not the same? The separate bucket that you made whilst you call the function has now been lost. So what we call is that these variables are immutable. Kind of a bad naming in my opinion, because immutable kind of suggests it can't be changed. Obviously it can be, like if you write x equals to 3 outside the global scope, or change it. But immutable refers to the fact that a function cannot modify. If you pass the x into the function, which is what we've done here, is not modifying it. Does that make sense? Okay. So everything we've learned so far are immutable. So x equals to 3, but x can be 3.5, and it wouldn't be mutable if you pass into a function. It can be a string, it's not mutable. If it can be a boolean, true, false, it's not mutable. Okay. What is printed here? So let's step through this. Before the function call, what do we print here? So what's the first thing printed? Yeah, 3. Good. And then we call this square number function. Okay, so now I made it even clearer that this is different. See how I've written this as n, as this as num? Because this is a completely new thing. Whatever you're passing into the function is its own thing. So this is n, where outside is num. Okay, so I can also write num is equal to num times num, but then that's a bit more confusing. So initially inside the function, the next line printed will be, yeah, good, 3 again. And then n is equal to n squared, so n is equal to 9 now. And inside the function, it's 9, which is modified. But after we leave the function, this n has been completely thrown out essentially. Like technically the memory is still there, but we just don't know where it is anymore. So we can't find that n anymore. So after the function call, what will num be equal to? Yeah, perfect, it's 3. So before function call is 3, right? Because it's here. Inside the function call initially, if n is passed as 3, so that's 3. And then inside the function here is being modified, so it's 9. But whatever modification we make here is different. So that is equal to 3 of the n. Okay, any questions about the scopes and mutability so far? Okay. So the last thing we're going to do is a pretty interesting exercise. It's like the random thing. It's quite a creative solution as well. So to get through that, we need to talk about why it's so important. So what we're going to do is hashing in a second. But let's try to solve a problem of searching through contacts. Right? If you want to find a friend's number from a long list of contacts, how would you do it? And let's pretend that you don't have your phone app, and then you write like a cue card with every person's name on the front and then the number on the back. How would you be searching through a specific friend? Let's say you're searching for Alex. Is there a good way that you can search through your pile of contacts and find him really quick? Control F, yeah. But it's like in real life, like pretend that you can't. But yeah, Control F. We would love to. Any other ideas? Throw them out here. These are names, so just alphabetic, like words, yeah. In real life, just a mess of cards. Like you have a cue cards of a bunch of people's numbers. Yeah, and then you probably put a pile that you done, and that's honestly the best way. We can't do anything more. So if you honestly get handed a list of random names to sift through, the best you can do is to go through everything, see if it is, like compare, like you pick up one. So what Python will be doing is pick up one name card, see if it's a name you want. If it is, yes, then if it's not, it puts it away. So this algorithm, and not really algorithm, but it had to go through everything, right? So the longer the list, the harder it is, because the more contacts that you expect to sift through in order to find the person that you want. So what we call that is a linear time complexity. On the x-axis, we have the input size, which is how many contact cards you got, and you're very popular with 550,000 contacts. And then how much time you expect the program to run will be here. So this is not really scale, but you can just imagine how many operations the computer would do, right? Because every single time you compare a card that you're searching through and the name that you want, that's an operation. So what we say is that when you have n contacts, the complexity is on the order of n. So basically it scales linearly. So if you have 10,000 contacts, you're going to have 10,000 operations. 30,000, you need to do about 30,000 operations. And this isn't exact, by the way. Like, for example, you might just be really lucky and halfway through, you will find the right person, right? But overall, you expect this is a scaling. So the longer your contact lists are, the more time that you will take for your algorithm to find everything. So the harder, basically the more intensive the calculation will be. But in real life, obviously we'll Control F. But let's say you can't do that, okay? So let's say you're trying to find a name. You wouldn't need to go through every person, right? Because your contact list is sorted by alphabetically. So let's have a look at yellow pages. Let's say we're trying to find Qua in the yellow pages. What we can do is very similar to the number guessing game we had at the start. So we will kind of go open the page and then see if K is after that page, right? And straight away, we will be able to eliminate half the book. So any intuitions if that's better or worse than our current linear sort? Yeah, better, right? Because rather than having to go through everything, every single time, every operation, it halves the amount of book space that you need to look through. So the time complexity here is logarithmic. So log 2n specifically, but it's like on the order of log n. So the volume of data, when it increases, can you see how the execution time doesn't actually increase that much, which is really important because if you're dealing with huge amounts of data, it will be really bad if the more data you have, the more time it takes to execute. And a really good example is, let's say 32 contacts. Let's say you met 32 new people, and then you now have 64 cards, right? But because it's alphabetically sorted, finding someone only requires one more operation. Whereas for linear sort, it will require 32 more operations. Might be 32, right? Because you have to look through every single person that has been added. So this is very good. How can we do it even better? So we're 2 minutes to just talk about it with your, see if you can implement a better strategy to search for contacts better than logarithmic. This is already very good, but how can we do it even faster? So hopefully you better have an idea. Bad.
They're like slacking, yeah. Slackers, bro. Nah, he said 2 minutes. I get 2 minutes.
Uh, yeah, yeah. So split it into small parts. Yeah. Huh?
Get the mic on.
Yeah, get the mic on.
That'd be crazy,
I don't know
right?
how to make this not suck. Hopefully it doesn't. Okay. Should be fine. Okay.
Okay. Okay. All right, we got the mic. I got the mic now, so I'm gonna go around to every
Oh.
table and ask for a solution. These guys are gonna.
Wait, sorry. Alex. Sure, it can be sorted. Yeah, it can be in any structure you want. Yeah, in any way you want. You can arrange it. Isn't part of it. So you can have your initial data however you want it. So we'll go like,
Okay.
we'll wait a bit. I think people, yeah. Dude, I read through that so fast. I didn't think it was gonna be like that fast.
Yeah, what? You
I thought it was like faster. Lucky I made this
You need to
part.
charge
Otherwise,
your computer.
oh yeah, are you one of those that you hate half charge computers?
No, but it was like 3%, bro.
Nice. I will survive.
I don't like seeing half charge. I don't like seeing that. Doesn't make me happy.
Okay. Okay, we're gonna get started now. Alex, Alex, Alex. Yeah, you can start. Yeah, ready to start. So you have 30 seconds to share your inventions. Should be. Oh,
So we thought about like grouping it separately. So we just said sort it alphabetically and also based on the length of the name. Because people think like Alex Borsman starts with A and it's full A as well. If you have like the letters taking up the same number of pixels on the screen. Have fun though.
okay, whatever.
I like it. I like it.
All right, just basically a dictionary with yellow pages. So it takes the first character of whatever you typed in, and then it goes to that section of the dictionary. So A will say Alex. We search up Alex, second letter L. So it goes to the subsection of the section A to go to AL. And then it
Yeah,
has say Alexander, Alexa, the other Alexa, stuff like Alexander. And then third letter, so on.
that's pretty good because rather than halving, we're doing like 1 out of 24, right? Yeah, great one. Okay, love that. Keep going.
Pretty much had something similar to like sort it alphabetically and then go off like the first letter. So on. But
Okay, great.
It's just alphabetical something. Something
Okay.
It's about making like a matrix the first two letters, so then you can, or even going in further as a location. And then Josh suggested also frequency of you accessing that person, that it would increase the probability of you finding the right people most of the time. That's going to be a more efficient system for you overall. Sometimes you'll have to search for a while, but most of the time you're doing well.
So that's a really cool technique called caching or memorization, which means actually it's an advanced technique that actually saves probably 90% of the population time. So when you actually work with this, you always want to cache because it means that you actually
For me, I'm thinking about like for example, if you have a contact, you have like Abby, Ab, things like that, you put like different hash, like different box with like Abby and all the names start with Abby, you put it inside there. And this may take a lot of memory, or if better, you can just put like all the names, like the box is just for Abby. So when you're searching for Abby, they will directly go to like memory pointed to that box. But just imagine there are so many names in this world, so it's not really possible there's that much memory to have each single hash like for every single name. So you can have more alphabet better lah for the like the variation A B C D F G Z, and the next, or if you want to make it better, you make it A B A C A D A E. So make it like different lists inside the box, so you can go search and find for it. But this one you take a lot of memory lah.
Yeah, really good. And that's a really important trade-off between how fast you want the algorithm to be and how much memory your entire contact will take. Yeah. Okay. It's really awesome to see all the solutions, but something that all the solutions have in common was that the longer the list, you're going to take more operations, right? Like even if you do it alphabetically, even if you split that load into like some different computers, and even if you do your table and then caching, it's all going to take like the more, it just has more data to sift through. We can actually do it even better. We can actually do it in constant time. So no matter the size of the data, the time to find the contact is the same. And this is basically as good as an algorithm can be. Because if it's better than that, it doesn't even run, right? So this is, no matter how long you're searching through, it's always the same. And that's what the functions we're going to be working on to finish today off. So let's say that we have a lot of buckets, okay? So this is basically, imagine a contact book, but rather than storing everything, kind of everyone's name, we can store them in numbers somehow. So what we need is that we need a function that takes names as input. So in our case, that will be strings. And when you put these strings into the function, it's going to distribute it to a bucket. So let's say that James, when you put into the function, is going to give you the code 745 to something like this. Alan will be somewhere else in the memory block. Bill will be somewhere else. Susan be somewhere else. And the reason this is so amazing is because you don't need to look through this anymore. You don't need to look through, like, for example, all these names one by one. You don't even need to halve the list every time. You can actually jump at the right answer straight away, which is why it's constant time. So it's kind of looking like, so the hash function is this thing. It takes a name and it gives us some random number somewhere. So, for example, if we ever look for James in the contact, we can put James into the hashing function and it straight away tells us where to find it. Does that make sense? So we're not actually looking through this anymore. All the other techniques, we're kind of looking through this and trying to filter this out. What we're doing is straight away taking the input, using the hashing function to tell us where we land, and then just land there to find it. So in terms of things that it needs to be deterministic. So no randomness at all. Every single time we put a James into the hashing function, we need to land on the same block every time. Otherwise, it's pointless. Every single time we use Ellen, has to land on the same block. That's how we can find it straight away. It needs to be uniformly spread because you can't actually have too many names in the same bucket. If you have like multiple names in this bucket, then it kind of like, it's really, it makes it easier still, but it's not exactly constant because, for example, if you have James here, you have Ellen here, and they both land in the same bucket, then you're kind of having to go through two things to find James or find Alex, for example, Alan, for example. So it needs to be uniformly spread. So for example, if you have 1,000 different buckets and you have 100 different names, you should try to have it in a way that if you, no matter what names you put down, it should kind of all go into its own bucket. It should be simple and efficient because that's what makes the algorithm great. Because we're not looking through this anymore. The reason it's constant time is because no matter how long this memory of our contacts are, if we just start with a name, it's just always going to tell us immediately where it is. And this should be as simple as possible. And this is actually, oh, I don't have the slide anymore, but this is actually kind of used other, like there's so many places used as well. Like, have you guys heard of like end-to-end encryption, for example? It's kind of like the Facebook can't snoop at your message, for example, because it's not getting sent as a plain text. It's getting sent kind of being messed up with encrypted with random numbers and letters. And you need to be able to have a function that decrypts that for whoever reads your message to be able to read it as plain text. So let's have a go at this. We take a string in as input, and then we try to say, give it from 0 to 100 as output. before we kind of set up on our own, anyone have any ideas of how we might try to convert string to a number? Do we need roaming Alex again? Okay. Okay, yeah, go. Oh, well, we need to make the string a store, make the name, which is a string, store as a number, right? So for example, if your buckets are labeled from 0 to 100, if we put down like 10 names, you would expect 10 buckets to be filled. Does that kind of make sense? So James might map to 9, Alex might map to 7, which is how this is so efficient because we can immediately find the right bucket. Wait, I think you're overcomplicating. All we need to do is to take this. So it's like, you know, the old like function, this is kind of like methods, but so function can take the domain is like a string, right? And then the output, like the range essentially, is a number, say from 0 to 100. And that's what f of x is. Does that make more sense? Like that's what a function does. It takes one data type as an input and puts another one outside. So something that you might is interesting to know is that there's actually something called ASCII table, which is how initially we store everything. So you can actually probably find a Python method for that, but every thing you put, for example, this letter uppercase A actually has a value of 41, lowercase a has a different value. So see if you can do something with that. Huh?
Unicode ASCII.
Wait, was that not ASCII?
Try all this. Or does the same thing. Is Unicode the same as ASCII or not?
Unicode's an expanded version.
So it's got more
Oh, yeah.
numbers. Okay. Yeah.
But it's the
Same
subset.
concept.
Yeah,
Yeah.
it's a subset.
So this is a function that you can try to use. See odd, it converts the x to the number. Oh yeah, h. But the variable is stored in the bucket of x. Yeah. Okay. No need for roaming Alex. Yeah. By the way, so odd only works for one character. And if you want to split a string into a lot of characters, you can actually do something like this. So let's say our X is James. We can actually do a for loop for each character in X, which is for a character in James, like this. We can actually separate in the individually. So that means we can do print so this is how you can separate all the characters, because otherwise you can't put into OR. So for character in string, every single time, the first time I'm taking the J, the second iteration of the loop I'm taking the A, the third iteration I'm taking the M, the fourth iteration I'm taking the E, and the fifth iteration I'm taking the S. Just so they can use all doesn't take Excel character. Huh?
What's your example?
This.
As in, like, what's the example? You don't know. Ah, okay. I can show you. Okay. All right. Okay. Just basic.
Yeah.
Yeah.
We're gonna I don't know.
I can talk a little bit about.
You can talk about don't talk about that. Do you want to take over this part?
No, it's fine. I kind of. Actually works is basically just select randomly from a family of primes,
Oh yeah.
and then you just like modulo it, and then that's it.
That's it.
That's a perfect hash.
Oh
function,
wow.
yeah.
So
Yeah.
any prime.
Yeah.
Oh wow. Okay.
And that's O1.
Oh wow. That's
That's
crazy.
how you-
Okay. making this function. I'm going to do a hash function right now,
Okay.
and they can
Copy, I guess.
compare how well distributed this is comparing to me.
Where they get the list of names.
Yeah. Oh, I'll just like they can try to beat me to be more
Yeah,
even
okay.
distributed.
What,
wait.
what method are you using? Just the sum of all the
No, name
sum of all the characters.
for
Name error.
name in probably
You're just summing up all the values in the name. I think we don't have any value.
Yeah, of course. Yeah. I'll try and do like a visualization of how good a function is. Forgot how. Oh, it's not doing the right thing for me. Does this just work? Nah. I'll probably spin it now. Oh yeah, this is pretty good. Okay. So it worked. Yeah, of like the relative frequencies of my names. The relative frequencies of my names. Okay.
So what have you pulled up with?
So common names.
Yeah.
My hash function.
Yeah.
This is what the distribution looks like. It's not that even. So
Huh.
I'm inviting other people to have a
You
go.
use a modular? How'd you get into the buckets?
It's just a very simple one. Okay. I think honestly, delete this one might be better.
Hmm.
Can I have your mic?
Yeah.
So if you have a hash function, can you bring your computer here? And I actually just coded up like a quick visual demonstration of how good hash functions are with a list of 100 most common names. So just bring your computer up here, and then if it's a different function, I'll just type it in my code, and we can put it on the board of how good your hash function is. Yeah. Did you send? Where did you send it? Messenger. All right. Anyone else? Wait, have you guys got iPhone? Anyone else? Okay. So we might just have a look and have a context of hash functions. I was expecting hopefully more functions, but it turns out most people did the same thing, which is what I've done. So this is the benchmark. I had the sum as 0 initially, and for every character, I basically increment the value of the character, and I just return that mod 100 to make sure that our output is a number between 1 and 100. Dolita did something pretty similar, but rather than joining the numbers by addition, she actually joined it by putting it onto each other. For example, if my one is 35 plus 36, it will end up as like 71. But the other one is 35 plus 36 in this way. So it will actually be 3000. So it will be a pretty long chain. So let's see which one is more even distributed. So let me load. So I found the 100 most common names to test it out. This is my solution. And then we can plot what it looks like. So would you say this is a pretty good hash function? It's not the best, right? Because a lot of collision. So see how this one, it means that this number here this bucket has 4 things in it. So basically what that means that when we go here, there's 4 things to look through rather than getting the right answer straight away. Okay, any intuition on Dolita's one? So drum roll, please. Okay.
Yeah, it'll be much better.
Okay, so big talk. Let's run it and see how it looks. So it looks pretty random. Like, I can print out the results here. So, yeah. So you can see that a lot of numbers, a lot of things are actually at the end. So it's pretty unfortunately distributed. But the part of the reason is because if we look at the name, a lot of the names actually end in something common, like for example, S or something like N, A, for example. So like there's a lot of letters that they're common. So when you add the value for S, for example, every single time it might end up when you mod 100, it's going to be very similar because does it make sense how like only the last couple of digits of his name actually contributes to the hash function? So it looks really random. Like if we put say name to key, if we put like James and we don't return the mod, it looks really random, right? But my intuition is that anything that ends with ES, for example, will all be 15. So let's try that. What's the name that ends in ES? Oh yeah, good one. Charles. So this probably will end up like 1115 as well, which is the case. So basically the reason for that is that so Charles like CH is responsible for these two, so on and so forth. But my one, it just adds it all up. It's actually the simpler solution. This is more complicated, but could actually work out better. So let's try my hash function. So Charles is very different to James. Oh, Charles James, sure. But yeah, so this is giving it a more even spread. So as you can see, a lot of names might end in something like this, and therefore all of them have like a 97 when you mod it. Don't talk about the state of the art.
I'm sure a bit about what's actually happening in the real world. So, because we're dealing with distributions, right? You ultimately want to deal with a randomized algorithm, which is an algorithm that actually inherently has randomness in it. So, for example, it uses like the RAM library. Best practice right now is actually to use what's called prime hashing function. So basically you have like this whole set of randomly selected prime numbers, and then you just like randomly choose a prime number and then divide the ASCII value, for example, or any other value by that prime number, and it actually evenly distributes it. Right? So it's actually not that complicated what state of the art is, but that's what state of the art is.
So yeah, the simpler, the better. Okay, so that's it for today. Thanks for coming in. We've covered so much content. Anything
Yeah.
else?
So if you're finding today a little bit difficult, right? There's just stuff you don't understand. Please, you're welcome to stay back and we're happy to explain some stuff, because I think tomorrow, Thursday, is going to get harder in terms of the difficulty of some of the stuff we're going to cover.